So in the past, we've indicated the direction of the E field, or the electric field, and the H field, or the magnetic field. We've indicated these directions by using the concept of the unit vector. We say that the field points in, let's say, the a hat x direction. So we may have a field and it's got its direction pointing in the ax, and we may say that we've got the magnetic field and maybe it's pointing in the ay, which tells us that the power field is perpendicular to both those, so it points in the z direction. So far we've been using these concepts of unit vectors, and these are very important when we're performing mathematical calculations about the field directions. But more commonly, when we're just discussing electric and magnetic fields, the concept of polarization is employed. And polarization is the description of the direction of a field relative to the surface of the Earth. And we will, when we're talking about polarization, we are interested in the direction of the E field. So polarization, it's the direction that the E field points. We'll say it's relative to Earth. There are two basic types of polarization. There are the one that you would expect, which is linear polarization, which means that the electric field vector orientation remains constant as it travels away from the observer. It could be polarized up and down. It could be polarized left and right. It could be polarized at a 45-degree angle. But the point is that the EM field points, it continually points in the same direction. It doesn't change as the wavefront moves. That's not the only type of polarization, though. There is also what is called elliptical polarization. And what is happening in elliptical polarization is that the electric field vector, the direction that is pointing, is actually rotating as it travels away from the observer. So if we were to point little arrows at the tip of the E field, it would trace out an ellipse as it travels away from the observer. Actual elliptical polarization is somewhat uncommon, and more often what we will see is what is called circular polarization. So if I were to watch the direction of the E field as it moved away from an observer, and I were to trace the shape that that moving E field direction makes, I would see it forming a circle. And so we've got linear polarization, and then we've got elliptical polarization. The most common form of elliptical polarization is circular polarization. So let's first talk a little bit about linear polarization, which is probably the most common type of polarization. And there are two types of linear polarization. There is vertical polarization, in which the E field vector is perpendicular to Earth. So we've got the E field, here it's indicated in red. Perpendicular means it's intersecting the Earth at a right angle. So if the XY plane here, I think that's XY, maybe that's actually ZY. If the ZY plane represents the surface of the Earth, in vertical polarization, the electric field arrow points perpendicular to it. So this is vertical. And the second type of linear polarization is when the electric field vector is parallel to the surface of the Earth, and this is called horizontal polarization. So we can see this vector here, this plane here represents surface of the Earth. E field in vertical polarization is perpendicular to it, and then if this plane represents the surface of the Earth, the E field direction here is parallel to it or in line with the surface of the Earth. Other types of linear polarization do exist. Here you would see if the YZ plane is the surface of the Earth, here we have a 45-degree linearly polarized E field. This is just not particularly common. It's possible, but not common. In this class, we will deal with vertical and horizontal polarization, not angular linear not any form of angular linear polarization. So the next type of polarization, the other type of the two, is circular polarization. And a circular polarization, it's the most common form of elliptical polarization, as I said earlier. And in circular polarization, the tip of the rotating electric field vector will trace a circle in space as it travels away from an observer. So you can see in these directions what's happening is we've got the direction of propagation, and the tip of the field is moving as it rotates. So we see that as this field is rotating, the E field is spinning around the direction of propagation. So you got to imagine that this vector is spinning like the second hand on a clock around this axis of propagation as it moves. So it's actually forming a helix, but if you were to look at it in 2 dimensions, it looks like a circle. There are 2 types of circular polarized waves, and that is depending on which direction the E field is spinning. There is right-hand circular polarization when the E field vector is rotating in the clockwise direction. So we've got right hand, and that's clockwise. And then I think you could probably guess the other type of circular polarization is left hand, and that's when it's counterclockwise. So circular polarization for antennas is actually fairly common, so this is a concept that at least right now you need to understand that there are 2 types of polarization, linear and circular. In later lectures, we'll study the impacts of polarization matches and mismatches on antenna transmission and reception. But for the rest of today, what we're going to analyze is just different cases of linear polarization.